My name is Kelsey Jordahl. I'm a geophysicist by training. I work at Planet Labs now. We design, build, and operate our own constellation of Earth-observing satellites. So I'll tell you a little bit about what we do and specifically what my team does with the data that comes down. So Planet's mission is to image the whole world every day, making change visible, accessible, and actionable. So that's our big picture mission statement. So imaging the whole world every day, that's what's really different about what we do, and I'll show you how close we are to actually achieving that. So I'll talk a little bit about our main platform that we're using to do this. This is sometimes called a nano satellite, a small satellite that's only about a foot long, 30 centimeters by 10 centimeters by 10 centimeters, plus solar panels that stick out a little farther when they're deployed. We also operate two other constellations of satellites that I'm not going to talk about in any detail today. The Rapid Eye constellation of satellites, there are 5 Rapid Eye satellites that are similar resolution, and also the SkySat or Terabella constellation that is higher resolution. I'll show you, I think, one example from the SkySat satellites, but for the most part I'm going to concentrate on the Dove spacecraft, which are the ones that Planet Labs was founded around building and operating, and the one that the constellation of satellites that we're coming into its full potential right now. So what do these satellites look like in orbit? This is a picture of the snapshot of our approximately 140 satellites that are orbiting the Earth. This is a little bit dated, but if you look at a current snapshot, you get something similar. So we have 2 different families of orbits. You can see the sort of lower sine wave. I have, here. That's an International Space Station orbit, inclination about 52 degrees. So it's limited. It can only image between those latitudes. It also varies the time of day that it looks down. Our production satellites are in this higher inclination orbit of about 81 degrees inclination. That's a more typical Earth-observing orbit, a synchronous orbit. So most of the satellites we're operating now, about 100, are in that type of orbit. So this is also not quite up to date, but an idea of the images that we were collecting towards the end of last year. I'll show you some more up to date things just shortly. Here, some of the data is you can see between the 52 south and 52 north in the space station orbits. We were getting more data last year. Now that's increased quite a bit. I'll show you how much that's changed in the past 6 months or so. So here's a graph that's up to date of the land area, the surface area that we're collecting images every day for the past year and a half, a little bit more. So here we have time on the x-axis from the end of 2015. The blue, under the blue curve are the 3-band satellites that collected only red, green, blue information. Since then, we've been launching pretty much exclusively 4-band satellites that have red, green, blue bands, and also a near-infrared band that's outside the visible range. So we have 4 bands of information, and now almost all the data that we're collecting is 4-band data. So if you look at this in millions of square kilometers per day. So we were sort of in the tens of millions of square kilometers a day, the beginning of 2016, sort of around 20 million through most of the year. Then a couple things happened in 2016, 2017 that changed this. So the end of June 2016, we launched 12 satellites in a polar orbit on the Indian PSLV spacecraft, and that is this ramp up in data for the last half of, or say the third quarter of 2016. We got up to about 50 million square kilometers a day, and then in February of this year, we had another launch that was 88 satellites, also on an Indian PSLV, and that's been this increase in data rate. And now the images we're bringing down are more than the surface area, the land area of the Earth every day, right? So we are there in that sense that it's about 150 million square kilometers per day. That's the area of the Earth. We're above that now. It doesn't mean we're imaging everything every day. There's some overlap. We're also imaging some oceans, things like that. So we don't get a picture of, and I should say, clouds. I'll talk a little bit about clouds too. But we are getting more than the land area of the Earth downloaded from space every day now. So we are there in that sense. So I'll talk a little bit about this launch that was this year. This really brought us to the current capacity. So I said this is in February. Launched on an Indian rocket into a polar orbit. And let me see if I can play this. All right, so this is a short video of the deployment of these. Sorry, I gotta skip ahead. Here we go. All right, so there's a rocket launch, and then the deployment of our 88 nanosatellites. Here they go. This is an onboard video camera in the launch vehicle. So you can see these are basically just being deployed out here, tumbling in space. We then deployed the solar panels and gained attitude control and so on after that to communicate with them. But this is them, the largest deployment of satellites in history, the largest launch. 104 satellites total on this single launch vehicle was a record, and 88 of them were ours. So they keep coming. You can see the front antenna is already deployed, but the solar panels aren't yet. All right, and then they deploy on the other side here. And they keep coming. All right, so there's still more, but you get the idea here. All right. So let me talk a little bit about our imagery. So I said all of these satellites that were in these last two launches are 4-band satellites. So they're imaging in the visible spectrum in red, green, and blue wavelength bands, as well as the NIR, near infrared band. So we actually do that in two halves of the sensor. We have to put those back together afterwards in post-processing. But it looks like this. We're imaging overlapping rectangles in one band and in another band, and then we stitch them together to build a 4-band product. So this is what everything looks like. Most of what I'm going to be talking about today is only in the visible, but we have the infrared information available as well. So I'll show you a few examples of our data, things that we've seen that are interesting and newsworthy in recent months. So this was the end of last year. the Oroville Dam in California. This was an image taken before the failure of the spillway and after this spillway failed and eroded a new channel. We've actually since got some images of they're reconstructing this, and we're following along as they rebuild that spillway and re-architect that as well. Here's an example of a large glacier collapse in Tibet. So this is before and then after. This is a debris field of a large ice failure and debris that spilled out over this plain from the glacier that collapsed. The scale on that is about 10-15 kilometers. This is just this week. So this is actually one of the high-resolution SkySat satellites that I mentioned, but I'm not going to talk about it in any more detail. But this was in the New York Times this week as an example of construction in North Korea. This is an image from an airport in North Korea that was acquired at the end of last year. And then one quick example of what you can see when you have many images sequentially. This is a series of images, I believe it's 33 individual images taken over a few month period. This is just off Cape Hatteras, North Carolina, and showing the formation of a new island earlier this year. So these are the kinds of things that we aim to be able to see and bring out with our data. All right, so let me talk about what my team does at Planet, and that's specifically turning all of these images that we get into maps to be a coherent global view of the surface of the Earth. All right, so this is a picture of the surface of the Earth, right? So this might be what you think of when you think of what does the Earth look like from space. This is what you see on all these web maps and what we all know of as what the Earth looks like, right? But this is actually a very artificial product. This one isn't ours. This is from the blue marble generated by NASA from MODIS satellite data. I'll show you examples of ours in a few minutes. But this is not actually what the Earth really looks like from space. First of all, we don't see through the oceans. You don't see the ocean topography. But most of all, you don't see most of the surface of the Earth either. So this is what the Earth actually looks like on any given day, right? This is an image from this week from the MODIS Terra sensor, just taken over the course of one day. So this is a typical day on Earth in July, right? So this is what it looks like. How do we deal with that? We're taking our images all the time, everywhere. But even if we imaged everything on the Earth on this day, you can see, well, you've got a few clear patches in North America. You got North Africa. A few places in South America, Australia, not much in Europe, some parts of Asia, but not the North. So it's a little bit messy. So our job is to turn that into one single coherent picture. All right. So let me just talk briefly about the tools we use to build mosaics. Since this is a PyData conference, I'll talk a little bit about the relevant PyData tools. So everything that we use in our workflow is based on open source tools. So we run our whole pipeline in Python with various parts in compiled C, C++ as well. The heavy lifting of the computation is in Jordahl. So the Jordahl is the geospatial data abstraction library. If you've done any raster manipulation in open source tools, you've probably used something based on Jordahl. Frank Warmerdam, the original author and maintainer of Jordahl, also works at Planet Labs, so he's the architect of our pipeline as well, so we have a lot of help on that. And then in addition to those tools, we use many of the standard tools in the Python stack, NumPy and SciPy and scikit-image, and then Rasterio, which is a set of wrappers around the Jordahl library that are more Pythonic. For various other things, we use many of the other tools you're familiar with in the PyData stack as well, but these are the main ones that are actually in the production in our pipeline. So happy to talk about how we use some of these if you're interested. First of all, let me just talk a little bit about how we do our mosaicing. So just in general, there's two main problems that you have to do, that you have to solve in order to build a seamless cloud-free mosaic of the world. Those are scene selection and color normalization, just to regularize the scenes to put them together. So first, scene selection. Every scene that we're taking, each individual take from a satellite is roughly 20 kilometers wide by 10 kilometers long. So it's a rectangle of a couple hundred square kilometers, and we're taking many thousands of these a day. So if we're making a mosaic from some time period, we have to select all the images that are available. First search for all the images that are available for a particular location. Then we have to rank them according to clouds and other metrics, sharpness, other sensor quality metrics, and choose the best ones that we have available in order to stitch them together into one seamless picture. So here's an example. We might have 25 images to choose from that overlap this tile that we're building in various ways. We select the two or three best ones that are going to fit together to give us an image, in this case over central Beijing, and stitch them together to make them one piece. All right, so that's one hard problem. We've got some cloud metrics, we've got some sharpness metrics, and we might also rank by the target date, how close it is to the center of the time window, and things like that. But once we've selected the scenes, then that's only part of our work. Even if we've selected them well, then we have to do some normalization on those scenes. And then this is an older image that shows some of our older satellite data that has a smaller footprint, but it shows the variation in colors in different satellites, but especially in things that are taken on different days. So just due to atmospheric variations, you get huge differences in appearance of the Earth taken through different conditions of haze. Mostly. In the early days, there were also some differences in the filters that are on the satellites that we're taking images through. Now the production satellites are pretty uniform, so that's much less of an issue. But these atmospheric conditions still matter. So you can see some look bluish and some look pinkish, and there's not the same color curve applied to all these things. We have to turn this into some regular appearance of what we think the surface of the Earth should look like. So I'll talk about one method we've used to do that. It's called histogram matching. This is a pretty common normalization method from photography. So you have a color target, and you have a reference image in this, and you have a source image, the image that you're trying to regularize. So you want to tune that source image to match the colors of the reference image. You do that by shifting the histograms of each color, that is each band, in this case red, green, blue visible bands, to match the cumulative distribution of occurrence in that. And that's a good way to normalize things in general. There are some issues with that, though, and that is, well, one of the biggest issues is things change on the ground. and if your color target, what you're matching things to, isn't exactly what things look like now, you're going to make mistakes. So here's an example. You've got a color target that is brown. So say it's a fall color target, and the hillsides are brown, and matching blindly to that brown color target, you get something sort of washed out and brown. But if you look at what the image actually has, there's snow in this valley, right? So that histogram matching is a pretty poor match to actually see what's on the ground. And one of the things we're interested in is change. So to make that change visible, using static color targets will mask some of that change, make it harder to see. So we've developed a new method that's better at showing, at regularizing images without changing their content as much. So this is a parametric fit that we've made for the same image that still matches the brown of the hills and the trees without leaves, but brings out the white in the valleys as you'd expect with snow on the ground. So that parametric fit is, well, I'm not going to talk about it in any detail, but if you're interested, there is a talk at SciPy in Austin next week. I'll give you the schedule for that at the end of this talk. But that's a more principled way to do this matching in a robust way that's not going to distort the data and just regularize things in ways that we understand. Okay, so that's how we solve the normalization problem in general. We also use color targets we build our own color targets to decide what we're going to normalize to. So a nice source of color targets is the Landsat 8 sensor. So this is a global summer color target. So summer, northern hemisphere, southern hemisphere, minimum snow and ice for the world. We also build other seasonal targets to match at different times. So this is one of our sources for truth for what the surface of the Earth looks like at a given time, or in this case at a broad range of times, since the hemispheres don't match. All right, and then one other thing we have to do, even with the normalization, there's still the possibility of seam lines. So here we've got three different scenes that are visible in individual images. This image doesn't quite match this image, doesn't quite match that image, even though we've done the color balancing and they're roughly the same. This image is a little bit hazy, but it's more or less normalized in color, but there's still these seams visible. So one more step we do, we call gradient blending. You might think of this as feathering in some other context, but to eliminate those seam lines, we essentially treat this as a free boundary, well, as a boundary condition that we match values across this seam, and we solve it as a partial differential equation to smooth that out, and that's our seamless gradient blending. So that's the last piece of how we put everything together. Now let me show you some examples. So here is our global summer base map. So this is sort of our best of all time imagery, summertime imagery in the northern hemisphere and in the southern hemisphere. We're a little bit broader in the input in the tropics to be able to do that, but here we've mapped something like 95% of the surface of the Earth. We're missing mostly very high latitude ice in, well, Antarctica and in Greenland, places that we don't rectify the images very well. There isn't a lot of ground control to do that. So we do acquire a lot of those images, but they're not included in these mosaics. They don't add a lot to it. But the places where you see the ground, almost complete coverage everywhere, and we have it all globally matched there. So this is a sort of static mosaic that you might have seen for a base map in other applications, in Google Maps and things like that. That's what a lot of people stop with, the build the best view of the Earth. We're also interested in the time dimension. So since we're acquiring images on a daily basis, we want to show the dynamic surface of the Earth. So we're building mosaics not just once, but much more frequently. So this is monthly mosaics. So build up since the beginning of 2016, and they step through May, I believe. Yeah, I don't have June added to this yet, but through May of this year, there are 17 months of global mosaics. And you can see the increase in coverage as you go through 2016, as satellites are deployed, and then into 2017, even more. So we're starting out at something like 60-70% coverage at the beginning of 2016 over a month, and going to 95 to 98% coverage, what we're getting this summer. You also see a change in the early 2016 data. You see different orbits are visible there as well. So there we see the low inclination International Space Station orbits that look a little different every month. When that fills in, now these orbits are all high inclination sun synchronous ones in 2017. All right. And you can see places that are cloudy a lot, like the Amazon, like Central Africa. They rarely completely fill in a month, right? You still see some gaps. So we're imaging those areas all the time, but we're not actually seeing the ground, even if you take images very frequently. But the more images we take, the more likely we are to get that one clear day where you do see the ground there. So that is filling in those places. You can see in May, those patches are much smaller as we have more and more data. All right, so that's monthly. Now we're moving towards weekly. So this is only for the continental US. This is, I believe, 13 weeks of weekly mosaics over the continental United States. And here, you can see some gaps. Those are almost entirely due to clouds. We're imaging everything at least once a week, in most cases several times a week. But there are still some gaps in between where in that week we never saw a clear view of the ground. But we're approaching now, we're averaging about 95% cloud-free coverage globally for the world in a week. So that's what we're aiming for. We're as the satellites spread out a little bit more, we will improve that incrementally. There's a few other things we can do operationally to help that, but we're still limited by clouds essentially. So that last few percent is hard to get. All right, so let me wrap up with a few other things. I want to talk about some of the things that we're looking at doing next. So I showed you an example of weekly. We're moving towards producing those every week and globally, and we hope to have those as a product sometime this year that's available to customers. Another way to increase that frequency is, it's hard to do a daily purely time windowed mosaic because of that cloud issue that I showed you. If you look at just a snapshot of the Earth on one day, it's 50% clouds. So updating the daily mosaic every day just by finding the good cloud-free images and having a dynamically generated image where you have all the clear images from that day, and then you may go back the rest of the week, maybe even back farther in some places, and have a dynamic mosaic. That's another product that we are working towards having. And then one other thing is to use the fourth band, to use that NIR band and incorporate that into the mosaics. So all those things are at the top of our list to work on. Let me just close with a few things you can do to look at and to use Planet data. The first that is publicly available is our gallery. So planet.com/gallery. All the images here are Creative Commons licensed by SA. So non-commercial by SA, I believe. So these are some examples of PlanetScope images that are in the gallery. There's also our Explorer web tool. This is available at low resolution without login. If you create an account, you can zoom in and look at the United States in full resolution. And you can have access to high resolution data, I believe, in California. So that's another place to look at. If you're an academic, we also have a partnership program called the Ambassadors Program. So if you're interested in research programs, if you have an EDU account, you can contact us and set up an account for access to your area of interest, and we can partner on a project to use our data in a research project. And then finally, we are hiring. So if you're interested in a job at Planet, we have offices in Bellevue here and San Francisco. And we are looking for people in various roles. So look at our careers page. Then one last announcement. Next week at SciPy in Austin, there are going to be 2 talks by my colleagues, Amit Kapadia and Joe Kington, on some more details of what I've talked about here, the time series mosaics and the color balancing algorithms that we use. So those are both on Wednesday of next week in Austin, if any of you have to be there, and those will be available online after that. All right, so thank you for listening, and I'll take any questions with the time we have.
I'm going to try and run this around.
Yep.
Get my exercise today.
Hey, thanks. What kind of derived products are you offering? Are you doing any edge detection to, good vector products for industries?
Yeah, we're working on those things. There are people doing analytics with our products. So the analytics companies that ingest our data and resell things, and we're working on analytics ourselves as well. Change detection is high on our list. We don't have any current commercial products, but if you're interested in particular things, we'd be happy to talk to you.
Any other questions?
It's over there.
Oh.
Hi, I was curious about your cloud masking. Are you just throwing out areas that have like a cloud mask, like when you're getting like a thin cirrus level, or are you trying to do some sort of correction with that?
Yeah, for the most part, cirrus will get thrown out, but sort of light haze will not. So yeah, for the most part, if it's really obscuring the ground, for the mosaics purposes, we'll penalize them pretty heavily, and we don't end up using them if there's anything else we can use. Yeah.
Hi. If I heard you correctly, you said that a mosaic is composed of scenes that are not necessarily within the same temporal frame. So what is the range that you build those mosaics, and how do you reconcile that with a task of doing change detection?
Yeah, that's a good question. So we basically have two two different models for building a mosaic. One is the all-time best, those seasonal mosaics, like that first one that I showed you, and that could be a very wide range of input, and we're trying to use anything that we expect the ground to look more or less like the right seasonal target that we're looking for, but there may be months and multiple years in previous seasons of data that are used for that. All of the monthly and weekly mosaics I showed you, though, are strictly time-boxed, so everything is within that month, strictly not using anything outside of that window. There's certainly room to play with those two extremes and fill a mosaic with the most recent data, but fill in the gaps with previous things when necessary as well. But you're right, for change detection, you want to know strictly when things are there, and those time-lapse mosaics, the strict window ones, are the ones that have that. Yeah.
Hi. Right. Yeah. What do your API products actually look like? Do you provide just raw image data? Do you provide these mosaics as well to individual consumers or just enterprise?
To commercial customers, yeah, we provide access to any of these. Just trying to think what we certainly provide web tiles at certain resolutions to general customers, to general free users in the Explorer application. Yeah, but for full resolution access to the mosaics, that's a commercial product. Right. In terms of the products that are available, we generally have visual, 3-band products, analytic 4-band products that are processed to radiance and top of atmosphere reflectance that you can download through our API as a customer and as an academic user and as a free user in limited areas.